Hi, linear algebra students. This is a proof of a theorem that I presented in class that we basically discovered by just making a bunch of examples and looking carefully at the matrix. So this is the theorem. It doesn't have any special name, but it's actually very useful. If we have a matrix that's described by its columns, A1 to AN, all being vectors, then each non-pivot column is a linear combination of the pivot columns of A. Be careful of A, not of the row echelon form. And as a result, the span of the columns of A is the same as the span of the pivot columns of A. And the reason why this is very useful is to get a minimal spanning set. So to remove any kind of redundant vector from the generating set. So basically, we put the generating set in a matrix, we row reduce it, and we just remove all the non-pivot columns from the generating set. And we have a minimal set, a minimal generating set that spans the same span, right? Okay. This argument, I really wanted to put it on the board first because it's an argument that if you're not trained to it, it's a little bit hard to accept. What I'm saying here is that without loss of generality, we can assume that the pivot columns are actually all the last columns. And this is almost never true, okay? Why can we assume that without losing any generality? It's because if this is not true, remember that this coefficient matrix can actually represent this linear combination in these variables, okay? And the only thing we need to do is to, if for example, this term is a non-pivot column, we just revert the order at which we add term in a way that this becomes at the very end. Okay, so since this is a sum, we can change the order of terms around, so we can always make sure that whatever matrix we get with these vectors, the non-pivot columns will all be at the very end. It will make the proof much cleaner, maybe even possible. And then there's another thing we have to be careful. The proof is going to be different depending on if the non-pivot column is a zero column or not. Okay? So, or actually, no, we don't even need that. The only thing we need to do is, so if this is the case, okay, so suppose A1 until, let's say, AK are the pivot columns. And n minus k plus 1. So basically, the term actually AK plus 1 until AN are the non-pivot columns. Okay. Then in this case, we can actually write something pretty neat for the reduced row echelon form of A. Okay? So then, the RREF of A is, so first of all, we start from A1 to AK, and then we have AK plus 1 until AN. And by putting this into reduced row echelon form, I'll make my arrow straight, what we get is something like this. So 1, 0, 0. Then we have 0, 1, 0. And then all the way up until 0 over here. And then we have zeros. So, And then finally, we have a 1 here and zeros all the way. So we get this diagonal of 1s, okay? And then we have here C1, yeah, it's fair. C11, C12, all the way up to C, and now I have to be careful. Okay, so let's say that the matrix has m rows. We have this. So C1m, okay? Or actually, I'm gonna revert these. Okay, I'm gonna say 1 1, 2 1, and then m1. Okay. And then we continue like this until we get C, and it's going to be here n minus k. 1, C, n minus k. Oh, wait a minute. Okay, good. 1, n minus k, 2, n minus k, and then all the way down to Cm, n minus k. So in other words, we have like this is the reduced row echelon form of A. So these are all the pivot columns, so they correspond to A1 all the way up to AK. And these are all the non-pivot columns, okay, which corresponds to, that's it, AK plus 1. And here, here we have like AN, which is the same as A n k plus n minus k. And the reason I put the emphasis here is just to show you that whatever's here is whatever's here. Okay, so it's just to count the number of columns correctly that we do this. Okay, so that being said, it means that if C, let's call it CL, well, actually, like, that's it. If AL is a non-pivot column, or yeah, let's say the Lth non-pivot column can be written as a linear combination of the k pivot columns with weights. And now I can use my notation to actually write C, and here I have C1L, C2L, and all the way up to CML. Okay, and then since this is true for every value of L, this is true for every L of L from. So unfortunately, I have to erase this, but it's true for every value of L from 1 to n minus k, okay? And this means that every non-pivot column is a linear combination of the pivot columns, proving item number 1. So okay, proving 1 was really just the hard part. because once one is proven, number two is really just a byproduct. What it says is that since each non-pivot column is a linear combination of the pivot columns, they can be removed from the span using the spanning set theorem. Okay, so by the spanning set theorem, so every non-pivot column can be removed from the set of all columns A1 to AK without changing the span. And as a result, this proves item number 2. There you go. This is the proof of the full theorem. So if ever you have a generating set and you want to write the set as a minimal set that generates the same span, then what you need to do is to just take the vectors from that generating set, put them in a matrix, row reduce, and each non-pivot column you remove from the generating set. That's it. That's the way this theorem is used. I hope this was helpful. See you in the next video.